Hello, good morning. So today we're going to talk about the torsional moment, the torsional problems. So make sure that still we are talking about the one-dimensional problems. One-dimensional problems. Up to the last time that we talked about the uniaxial problems, where we considered the axial load, and then also we discussed the development of normal stresses and then the shear stresses depending on the observation directions. Today's subject is kind of extension of the discussion that we made up to the last time. Still, we are talking about the axial members, but the loading condition is twisting moment, so we want to consider the axial member here. But last time that we applied the load in the longitudinal direction, we call it in-plane loading. But here today, we're going to apply the torsional moment, so which means we'd like to twist my member under consideration. That's the subtitle of this lecture note is torsional members here. Okay, the first part is the outline. And again, here we have 7 different subsections in this lecture note. Each subsections may have one break, okay? At least one break to not to increase the time for the lecture, the video. So first part is the outline. So the learning objectives are, we'd like to study the twisting of circular bars, okay? And then a hollow shaft acted on by torsional moment. That's what we want to discuss. And then here we'd like to develop so-called torsional formula. The role of torsional formula is to make a relation between the shear stress and then with the radial distance measured from the center of the cross section. And then here, similar to the relation between the axial force and elongation that we discussed in the section for the axial members. Here we'd like to develop a formula for the torsional moment and then some displacement. And then here we'd like to find the stress development in these torsional problems. And then also we'd like to discuss normal stress and shear stress developed by the torsional loading. And then here we wanna drive the relation between the elastic modulus, the so-called elastic Young's modulus, and then shear modulus. Shear modulus, we denote the shear modulus G. This is another linear elastic proportionality coefficient between the shear stress and shear strain. In the case of uniaxial relation, the stress and strain. Let me check if everything is correct. Okay, so according to Hooke's law, this is a linear. The slope is called elastic modulus. So we consider the same relation, the shear behavior between the shear stress and the shear strain gamma, and then there is also linear relation. This is called the shear modulus, okay? And then this is called elastic modulus or Young's modulus. And then this is called shear modulus. In 우리말 탄성계수, 전단 탄성계수, or sometimes they call it just 전단계수. Okay. So here in this chapter, we'd like to find a relation between the elastic modulus and shear modulus. If shear modulus is independent of the elastic modulus, or there is one-to-one relation. So although we're gonna drive the relation later, if I give you the answer in advance, these two parameters are not independent of each other. So there is one-to-one relation between the elastic modulus and shear modulus. And then here, after that, we'd like to talk about the concept of the power transmission. Just imagine that you have an engine or motor. Then from the body of the engine, then typically we have a shaft here, and then the rotation produced by the motor or engines is transmitted to my wheels of a vehicle to transmit the power, isn't it? So typically the transmission of power is done by circular shaft by means of the torsional moment. So here we'd like to discuss the concept of the power transmission, and then we'd like to discuss the relation between the power and then torque, torsional moment, what I mean, and then speed. And then again, similar to what we discussed in the chapter of axial members, so we want to talk about the effect of reaction to discuss statically indeterminate shaft members, okay? Statically indeterminate problems. And then the solution approaches is still the same. So we use, still the same, the three conditions, and we deal with the problems, the conditions, one by one. Then we can solve the problem. Doesn't matter whether you are dealing with statically determinate structures or statically indeterminate structures. Okay. And then here we want to discuss how to calculate the maximum shear stress in non-circular shaft here. So this is kind of advanced subject. We'll discuss the nature of the problem rather than solving the maximum shear stress field. Okay. So basically, we don't want to study this part, the last one, but we'll see the characteristics. Now let's define the torsional problems. Again, as I told you, we are still talking about one-dimensional problems, isn't it? Yeah, one-dimensional problems, and then we have a member, the prismatic member. Especially in this problem, we want to consider circular section. Okay. When we discuss the axial members, then we consider the prismatic members. Okay, in the chapter of the axial problems. But here we want to consider not just arbitrary prismatic members, but we want to consider only the circular members or hollow members. Okay, so anyway, the cross section should be circular. Okay, or it's like a tube. Then whatever we discuss in this chapter should be applied to these circular members. Okay, it's limited to the circular member. This is very important. Okay. Otherwise, actually, we can apply the principles that we discussed in this chapter to just arbitrary cross sections, like for example, channel T sections or the rectangular sections, and then it's gonna cause some problems, which cause warping. Here we have warping problem. Okay. But in the case of circular section, no warping. Okay. Circular sections are only sections where we don't have any warping problems. And then what's warping? We'll talk about later. But if I give you a brief overview of warping, okay, let's consider this is my aspirin box. Okay, let's consider this box here. Then we want to apply the torsional moment. So if we apply torsional moment, okay, let me try to apply the torsional moment. So if you apply torsional moment, then we have, I don't know if you can see, so we have some distortion. Okay, let me see. We have distortion here. So this part goes up, and this this end goes down, and because of the difference, and then we have actual displacement, and this actual displacement produces secondary normal stresses. That's why the analysis becomes complicated. That's why instead of talking about arbitrary cross sections in this chapter, our discussion is limited to only the circular sections. Okay, this is a very important part that we have to keep in mind. And the first, let's talk about what's torsion. Torsion means, so we want to consider twisting of a straight bar when it is loaded by moments, thereby producing the rotations about the longitudinal axis of the bar. Okay, and then before this, the key point is here we have to consider the circular section. Okay, okay, only for the circular sections. And then here we have new terminology called couple. The couple means a pair of forces, as given here. Okay, a pair of forces which produce equilibrium. If you check the equilibrium in the horizontal direction for this, then sum of forces in the horizontal direction is equal to 0, but it produces non-zero moment, isn't it right? Non-zero moment with respect to the center of the member, and this is called couple. Okay, couple. And then how about this? If you look at this guy too, sum of forces in the vertical direction is equal to 0, and then but it introduces a torsional moment. And then how we represent the torsional moment. Torsional moment is also, we can represent torsional moments is, by using the vector concept. To represent the force, okay, for example, force, we use this. Okay, we need a direction, and then we need a magnitude, isn't it? This is how we represent the force vector. But how about moment? The moment can be treated also as a vector, but it follows a right-hand rule. For example, like this. So in the case of force, we use one arrow, but to represent the moment or the torsional moment, so we use double-headed arrows. Okay, double-headed arrows. And then the direction, where the double-headed arrow tip represent is the direction of my thumb. So we are using the right-hand rule. So to you, it doesn't look like my right hand. Okay. So direction of thumb. Okay, this is my right hand. Direction of thumb, and then this is direction of torsional moment. Okay, torsional moment. And then instead of this double-headed arrow, maybe we can just draw the direction of rotation directly using the circular arrow like this. Okay, so this is more intuitive. We can see the direction of the torsional moment very easily. But in this case, it's quite confusing, depending on who drew this arrow, we can have, we may have different informations. That's why instead of using this, I recommend you to use double-headed arrow. That's better. But that provides more intuitive information. And then the third one is moment of a couple, the product of one of the forces and then the perpendicular distance between the lines of actions of forces. Okay, then so moment or torsional moment or whatever. Okay, this is caused by the moment caused by force. So which means we need to multiply the arm length times the force. Okay, arm length times the force. So if you took statics, then this is well-known principle, isn't it, right? This is calculation of moment. So how about this? For example, say we want to calculate the moment with respect to this point. And then let's say this is my arm length L. and then my force is applied in this direction, my F. Then how do you calculate the moment? The moment is what? Just L times F. Okay? Let's consider another case. So instead of force in the perpendicular direction, but let's say we have force in angle theta here. Then what do? Then in this case, the moment produced by this blue F is equal to, we have to consider only the perpendicular component, okay? Perpendicular component. That's why L, the arm length is L. The perpendicular component of force is what? Force times sine theta, okay? Force times sine theta. Is it clear, right? As an extreme case, for example, what if you have force like this? Actually, in this case, the moment produced by this force is what? Arm length is L, and then the perpendicular component of force is F sine 0, isn't it? So this is equal to 0, okay? And then torque is just torsional moment. So moment produces the twisting of a bar or shaft. That is called torsional moment. Okay, torsional moment and torque, same. Torsional moment and torque. Okay, same. Do you have any questions? Then how to tackle this torsional moment, torsional problem? The principle is still the same. So we still want to use 3 different conditions. So force equilibrium and material laws and displacement compatibility. So this is just general representation, the relation between the stress and strain. But specifically now we have, instead of normal stress, we have shear stress. The shear stress tau, and then the strain, engineering shear strain. That's the only difference, okay? And how about here? Instead of force, we have torsional moment, and then tau. And how about here? Displacement compatibility. Instead of elongation, we'd like to measure the rotation, the angle of twist, and we want to measure the shear strain. Okay? So this is the outline. So let me take 10 minutes break.